This was so far has been an amazing performance, and I hope you agree with me. And also you might be asking yourself what it takes to perform so well, to play and to sing so well. And well, one of the things that happens in music, most music, is we squeeze so much rhythm into so little time. We have to make sure that notes arrive just at the right time in millisecond precision. And also, we have to make sure that the beat is right. And beat is a kind of little larger way of organizing notes together, and so that they arrive in the way that we expect them, at the right time. And there are also other things there. The phrases and the song might have a structure that evolves slowly during the song. So what I'm suggesting, what I'm focusing your attention on, is the way we're sensitive to things happening in time at multiple time scales. And one way to think of time scale is just what is the meter that they use to measure the time. I could use milliseconds, or if I start going up, might go to seconds and even more. So for example, we're also sensitive, not necessarily in the case of music, to bigger kinds of periodicities. That's the one that we're all familiar with. There's the one that we all know. We have to wake up, we have to go to sleep, and we drive through this cycle. It's so strong that we don't think about it too much, but it's also something that we're kind of entrained into. The experiments have been done where participants have been deprived of the light variation that is associated with the sun, and also with temperature. So they live in a constant amount of light for days, even weeks, and the same temperature. What happens is that their circadian rhythms start to desynchronize and they start to become longer. So their body doesn't know anymore what's 24 hours. And we know this is one of the first things that we learn when we're kids is these animals that are really, really sensitive, wouldn't be able to survive the winter, so they have to anticipate the winter and go to sleep before they get in a situation where they are awake but they cannot find food. And you could keep going up, but I'm not going to talk about it because that's not really our area here. So I'm starting to go down. Body movements are also very interesting, and they could take very different time scales. So for example, this apparatus that kind of looks like maybe a little scary, it looks maybe like torture chamber or something. These kinds of things have been used to, in this particular case, to perturb the jaw when it's moving to, and while the participant is saying a single particular phoneme or sequence of like ba. The person is saying ba, and the jaw is being moved up or down in an unexpected way. And in this case, they were interested to see how all the other muscles come in to compensate for the perturbation so that the participant could still say ba. And the interesting thing is, you could read the title there, you need more than 70 muscles. They have to be coordinated precisely just so that you could say ba. And now imagine you have to perfect this even more to be an amazing singer. So that's why we come and appreciate a great singer like today, because we probably were sensitive that how beautiful and how hard it is to be able to produce these sounds. So I'm not going to talk more about body movement, because if I do, then it will take forever. This is kind of my area. It's more interesting, maybe, what happens even lower when we go to what the brain is doing. So, for example, this is some work coming from our department. You could see neuroactivity. Something about the neuroactivities seems to be synchronized to an internal isochronous beat. So in this case, the participants, excuse me, the participants are being exposed to some kind of periodic auditory stimulus, and you could find with this apparatus that samples electromagnetic field on the surface of the head, you could find some activity that locks to the periodicity of the stimulus. So these are these waves, and the vertical lines are where the stimulus would be if it were heard. And we might be interested what happens even lower, at the level of individual neurons. So what I showed you corresponds a little bit to the wave at the lower left corner. This is actually a very, very aggregate activity of many neurons. What we record with these devices on the surface is actually the product of many neurons coming and playing something or interacting in some way and being there and doing something in synchrony. So you could see that neuroscientists make these little circuits, and they propose, okay, this kind of circuit will be able to do an oscillation, and this kind of circuit will be able to do something else. Usually the circuits are very simple, because it's just so hard, there's so many neurons. The thing that should start giving you an idea is the other figure that looks like dots is above the wave. These will be the individual events of neurons. Many neurons, they're kind of stacked on top of each other, and the x-axis is time. So you see, in this case, the neurons are firing relatively in synchrony. This produces this oscillatory wave that would be something that you record from the outside. And the really amazing thing, actually it turns out, for this to happen, you need hundreds of thousands, even millions of neurons. So that's when we record a brain wave. What's happening underneath is many, many, many neurons firing relatively in synchrony. So what's the common theme here? Across all these scales, what I'm kind of suggesting with these very simple examples is we always have periodicity, we have some kind of synchronization of something in our bodies to something outside in the environment. And what I'm interested, what is particularly interesting, not just for me, for many people, is is there a common mechanism? Most scientists are kind of trained to, we typically have been trained to focus in one level, right? One scientist will focus on this layer, another one on that layer, but maybe there's something that is shared in terms of an abstract mechanism, which is what I'm going to show you now. Now, the so-called science of synchronization might start with this particular scientist, 17th century. He was the inventor, and he discovered lots of things and also invented the pendulum clock. And this was a big breakthrough back in the days. This design was the most accurate for 3 centuries. Also, what he discovered, it wasn't his main work initially. The story goes he was very ill and just laid in bed and couldn't do anything, and saw that 2 pendulum clocks in his room were spontaneously becoming synchronized. And I don't have these kinds of clocks, but I have 2 small metronomes, and I'm going to show you the same thing happening right now. These are metronomes, and what's good about them is that they're mechanical. Because they're mechanical, they can push each other. So they're similar to each other, but they're not very well synchronized, right? I hope you can hear. Now what I'm going to do, I'm going to put them in a situation where they really start to interact more strongly by placing them on these coke tins. And I hope that they won't fall. Now, I don't know, it's kind of far. If you could see the platform has to move. And that's very important. And if I take them off and put them on a stable ground, slowly they will start diverging. We don't have time to wait for them to diverge, but if I just put them a little bit, they will not synchronize again. Okay. Now, what is the trick? What's the interesting mechanism here? Is this positive feedback that's happening through the collective behavior. In this case, the collective behavior is the whole platform. The more the two metronomes become synchronized, because their mechanical forces kind of go together, they push the platform more. And now the platform is in return pushing them more. So you get this feedback, a circular kind of causation going up and down between the individual units and the whole thing together. And this is what drags the individual units into synchrony. You might say this is not really collective because it's just two. That's why I made you a little simulation to show you more. I don't have that many metronomes, but I could just put them on the screen with the simulation. What's happening here is you see, in addition to them being, there's many of them, these ones are bad because they're variable. They're not good metronomes. And the thing that corresponds to the collective is this blue thing in the center. It's just the average of all the units. And what you see is that when I start increasing here how much the units listen to each other, as this, which is the collective, the group starts to increase, they all should start synchronizing as well. So start the simulation. Or so at the beginning it's kind of random, and basically now they're just going crazy on their own. And the coupling, now they start to listen to each other, the average field you can see increases. Now they're locked to each other. And there's one strange, the strange one doesn't listen to the rest.
Black sheep.
And again, when the coupling is removed, they'll again do desynchronized. Now the important thing here to notice is that they not only became synchronized, if you notice, they became more regular. So now in this system, there was no clock. They were all bad metronomes. But when they were forced to work together, in this case, mathematically, I don't want to bore you with the equation, but the simulation just illustrates how they're pushed into a periodic behavior. And this is something that usually you see as lesson 1 in the course in complex systems. So today you just took lesson on the first day of complex systems course. And to finish this, this approach has been applied to collective behavior in animals, usually animals that live in groups. And either you can study fish or birds or many other things. Humans too are actually often do things in group. Prayer, protests, chanting. Like I alluded already, this approach is maybe the most important is in showing what happened inside the brain, how all these neurons happen to, how they manage to become synchronized. So the work that I'm showing is just a little example of much more serious modeling and application of a serious experiment, some of which target situation where synchrony is not good. In Parkinson's disease, for example, a part of the brain becomes too synchronized and does not let anything else happen, in which case the goal is to use this theory to actually desynchronize this part. So the work in that case is to desynchronize, not to help synchronization. No. Should I do the demo? Okay, so the last thing that I did not talk about was speech. Speech, as you might have noticed, doesn't have the same kind of rhythmic nested structure as music. It doesn't have beat, you cannot just break it into equal parts. But when people have to speak together, something strange happens, and I'll try this with you. So I need 4 volunteers who read the text from the screen out loud, individually, and then you read it together in synchrony, and you'll try. So who wants to try this? I see 1 volunteer, 2, 3. Okay, 3 is enough. So start from there. There's actually maybe 2 of them. So I will not, initially I was thinking of actually recording you doing the analysis on stage. It's too much. So now we'll just do it without analysis. What we'll do is, I'll show the text on the screen. Participant number 1 will read it. Then participant number 2 will read it. And 3, I'll just point, but please raise your hand so I can see it. And when we're done with individuals, you do it together, okay? So starting from there.
The Hamilton Bulldogs are a major junior ice hockey team in the Ontario Hockey League that began to play several seasons ago. Based in Hamilton, Ontario, the Bulldogs play their home games at the First Ontario Centre. They were purchased in and relocated to Hamilton after a 34-year run in Belleville, where they were known as the Bulls.
Okay, that's enough. Who is the next one? Yes, please.
The Hamilton Bulldogs are a major junior ice hockey team in the Ontario Hockey League that began to play several seasons ago. Based in Hamilton, Ontario, the Bulldogs play their home games at the First Ontario Centre. They were purchased in and relocated to Hamilton after a 34-year run in Belleville, where they were known as the Bulls.
Okay. Third, yes, please.
The Hamilton Bulldogs are a major junior ice hockey team in the Ontario Hockey League that began to play several seasons ago. Based in Hamilton, Ontario, the Bulldogs play their home games at the First Ontario Centre. They were purchased in and relocated to Hamilton after a 34-year run in Belleville, where they were known as the Bulls.
Okay. So now it will be good to have maybe 4. So the 3 of you and 1 more enthusiast. Okay, so 4 of you. This will be really hard, I know. I'll start, and you have to start with me, and then I'll let you continue on your own. I'll just read the first 3 words, and then you have to continue. And I want the rest of you to listen to them and just see if this is not the perfect controlled experiment, because I tell you what to listen for, but pay attention to the rhythm. So, I start, and you follow me, and then you continue. 1, 2, 3.
The
Hamilton Bulldogs
Are a major junior ice hockey team in the Ontario Hockey League that began to play several seasons ago. Based in Hamilton, Ontario, the Bulldogs play their home games at the First Ontario Centre. They were purchased in and relocated to Hamilton after a 34-year run in
Okay, by the end things became a little complicated. So, this is the end. I'm just curious, did you hear?
Yes.
Did it sound like they're more in some way paced?
Yes.
Okay. Well, that's the premiere of this demo. And now I'd like to invite Dan and the band back to stage to now really hear professional musicians and not like us trying to speak something silly.